Okay, so I wanted to cover a question that has come up a few times, both online and personally with myself, and that is in the world of OTA, in the world of cord cutting, in the world of catching TV stations by antenna, what does a signal amplifier do? Okay, so it might sound obvious, but perhaps it's not. And what I'm going to do here is show you what is the effects of a signal amplifier and when would you use one? That's the biggest question, right? Okay, so what we have here is a spectrum analyzer I have connected to my antenna. And what I've selected is channel 10 on the VHF high band. And this is a relatively strong channel in my area, and I never have trouble receiving it. And it's ATSC, so here in North America we use ATSC. And you can see this little peak here is what's called the ATSC pilot. And it's at about, well, it's showing 192 megahertz roughly. I think it's whatever it is. Anyway, so as you can see here, we have over here, we have what is basically noise. Okay, there's no adjacent channel in this market. And on this side, we have noise. And this peak here, across this whole area here, is around 6 megahertz, and that is the channel allocation for channel 10. ATSC uses 8 VSB as its modulation, and what that is a vestigial sideband. So you can just think of it as you have a carrier frequency, and one of the sidebands of that frequency is what's actually being transmitted. There's a little bit of the other sideband over here. That's why it's called vestigial, but that doesn't really matter right now. So we have pretty good strength here. The amplitude here is measured in dBm, which is dBs above milliwatt. Now, don't worry too much about the actual values here. I don't have a perfectly calibrated system, but it works well enough for what we're doing. Okay? Anyways, so what we have here is the pilot is reading about minus 74 dBm. So that's minus 74 dB below 1 milliwatt. And I will pop up what value that is in watts. It's very small, but that's fine. So that's what we have here. Now what I'm going to do is I'm going to disconnect this antenna, the spectrum analyzer, and put in an amplifier. Okay, so now we have basically nothing. We just have the noise floor of my spectrum analyzer because nothing's connected. Now this amplifier is, I think, spec'd at 26 dBm. dB, I mean. I'm not quite sure, but it doesn't really matter. All right, so I have the amplifier connected, but I don't have it turned on, and you can see, well, it is interesting because you do see the peak here, but it's at minus 99 dB. So, without the amplifier turned on, it's, as expected, it's attenuating things. So I'm going to turn it on now. Okay. So here we go. So you can see things don't look that different other than the fact that everything is higher, right? And if you look here, we check our pilot, ATSC pilot, it's now at minus 57 dBm. Before it was at minus 74, I think. So yeah, there's about a 20 dB amplification here. But here's the important bit. Notice that while everything is higher, everything is higher. So while our signal, our 6 megahertz ATSC signal here is higher by almost 20 dB, notice the noise is also higher by quite a bit. I had the noise floor just above minus 110 dBm before I put this signal amplifier in, and now we're seeing it, well, about 20 dB above that. In fact, if you notice, it's a little more than that. And that goes to what an amplifier actually does. An amplifier amplifies. Makes sense. but it also amplifies noise. So we have the signal being amplified here and the noise being amplified here. So why is that important? Well, while signal strength is important, signal to noise ratio is equally or more important in some cases. So what happens is, to receive a signal well, you have to receive the signal, but it has to be above the noise floor a certain amount. Now, for ATSC receivers, generally, this is just throwing numbers out there, but generally, signal to noise ratios of about 20 dB are where things start getting unfriendly. So if you have a worse signal to noise ratio of 20 dB, you might have trouble receiving that signal. So in this case, before the amplifier was put in, our signal to noise ratio, we had the ATSC beacon at minus 74 dBm, and the noise floor was around minus 105 dBm. That's a pretty good signal to noise ratio. You're looking at, 30 dB. But now with this amplifier in here, we're not seeing, we're seeing stronger signal. We're, minus 57 dBm, but the noise floor is at minus 85. And that's a degradation. Before we had about 30 dB noise ratio, signal to noise, and now we're looking at around 28, 27 dB of signal noise ratio. And why is that? Well, it does make sense, because amplifiers, what they do is amplify. They amplify everything. But what they also contribute to this whole equation is they introduce noise. No amplifier has no noise. Okay? It produces noise as well. And most amplifiers for, these sorts of amplifiers specify around 2, 3, 4 dB noise. And that's exactly what we're seeing here. We're seeing an amplification of about 20 dB, but we're seeing an addition of noise of around 3 dB. So while the signal is hotter, is stronger, the noise is stronger as well, and there's some additional noise. So we've actually degraded signal to noise ratio. Okay, so this all sounds horrible, right? Let me unplug the amplifier and go back to what things looked like before. So there's our noise floor with the amplifier. Actually, that's kind of interesting. So before I disconnect everything, here's the amplifier on with the noise. And if I turn the amplifier off, you see that drop? So that's interesting, right? All right, so now we have just the antenna connected. Again, signal levels are lower. If we check the beacon, we're at 76, 77 dBm, but the noise is lower. If we go down to the noise, we're at about minus 107 dBm. So we're still looking at 30, this is the 30 dB signal noise ratio that we were talking about earlier. With the signal amplifier, our signal noise ratio went down to about 27. So, sounds like we made things worse by using an amplifier, and frankly, that's going to be the result the majority of the time. All right? For most of the time, when you amplify a signal, it will make things worse. Okay, so why do these signal amplifiers work? One, marketing. People think amplifier good, therefore better. Okay, the second reason is they do exist for a reason, all right? So what can happen is, if you have a very long stretch of coaxial cable is not perfect. It will attenuate the signal, and the amount of attenuation is determined by the length of the coaxial cable and its composition. So I'm using RG6 coaxial cable here, which is actually quite good. It's relatively cheap these days, and it's quite good. So what happens if you have a very long run of coaxial cable, it can attenuate the signal so much that it drops below the sensitivity of your receiver. So if your TV receiver can't see a signal below, say, minus 70 dBm, all right, it doesn't matter what the signal to noise ratio is anymore. It won't see the signal. So that's what you use amplifiers for. If you have some attenuation in your system, be it a long run of coaxial cable or, the more common reason, multiple receivers. All right. For every receiver you add to your system, you drop signal strength for everybody by around 3 dB, depending on what splitters you're using. And it could be even more, but anyways, so that's where you would use an amplifier. There are devices called distribution amplifiers. They are an amplifier and splitter combined into one, and their specific purpose for existence is to split the signal of one antenna to serve multiple receivers. And that's a case where you might use one, because while you're degrading the signal to noise ratio, you are making the signal hotter. So by the time it reaches the receiver, you have a usable signal. All right, if there are any questions, please let me know. As always, stay safe. Until next time, bye.